So this is a pretty simple do now that I would have you guys do in class, and that is I've got 5 different examples here of either a bar moving along rails, or as you see in the third example down here, the rails are moving, being pulled while the bar is stationary, and these are all in a uniform magnetic field. Now, what I'd like you to do is I'd like you to consider the 5 scenarios and determine in which of the 5 scenarios would an EMF be induced in the loop. So EMF meaning a voltage induced in the loop that's going to cause a current to flow in the closed loop. All right, you'll notice that in each of the cases we have a closed loop. Okay, we have a closed loop of conducting surfaces, so we could, if we have a voltage, we could induce current to flow. So I'll give you an example of the 5. I'll explain what's happening in each of the 5, and then what I'd like you to do is pause the video before I go through the solution and see if you can determine which of the 5 would induce an EMF in the wire loop. Okay, so in the first example we have conducting rails. So this is your conducting rail, and it is stationary. And you lay a rod, a conducting rod, on top of the rails, and you're going to drag the rod to the right in this uniform magnetic field. Okay? So I want you to think about, is an EMF going to be induced there? Number 2, what is happening here is that the entire experiment has been done in a uniform magnetic field. Okay, so for example, in the first case, you'll notice that there's an absence of a magnetic field over here where the rails are. So only the rod is going to be moving into the magnetic field. There's no magnetic field here on the left side. In example number 2, the entire experiment is immersed in a magnetic field. In example number 3, it's a little bit more interesting. Instead of the rod moving, the rod here is going to be stationary, and I'm actually going to pull the rails to the left. So the rails are going to move to the left while the rod stays where it is. Okay. In number 4, over here, instead of now rails, I've just got a square loop. I've just got a square loop, and what I'm going to do is I'm going to take the entire square and I'm going to move it into the magnetic field. Okay, so the whole loop of wire, bring it into the magnetic field to the right. And in the last example, I'm starting the experiment completely immersed in a magnetic field. So I'm not entering a magnetic field, I'm already in the magnetic field, and we'll see if that gives us a different outcome. So what I would like you to do right now is I would like you to pause the video and try these for yourself before viewing the solution in a minute. Okay guys, hopefully you're back. Hopefully you tried these on your own, and I'll look at these individually, each of the examples one at a time. If I'm looking at the first example, I've got a bar moving to the right in a magnetic field. Well, if this is a conducting bar, and I'm moving to the right in a magnetic field, even though this bar is neutral, as I'm moving to the right in a magnetic field, I know that the charges on the bar are going to want to separate. Okay, so what I need to do here is I need to do a right-hand rule, and that is V cross B. So velocity is to the right, magnetic field is into the page. Notice that your thumb is pointing up. So that means positive charges are going to want to move up. And of course, then negative charges would move down. So what you've done is you've kind of made a capacitor out of this rod. Kind of. It's not really a capacitor because it's all made of conducting material. It's not parallel plates. But you have managed to separate the positive and negative charges. So what I would say then, for number 1, yes, we are going to induce an EMF. We now have a voltage on this bar, and the conventional current would travel counterclockwise, right? In the direction of the positive is what we call conventional current. So we would induce an EMF and we would induce current in the loop that is counterclockwise, okay? When I move to example number 2, really having this magnetic field on the left side doesn't change what happens to the bar. The bar is still moving to the right. If I do QV cross B, I still notice that the positives want to go up, the negatives want to go down, so I will induce an EMF. And again, the current is going to be counterclockwise, the conventional current in that loop. Okay? Now it gets a little bit more interesting. In example number 3, I've got the rails themselves are moving. Okay? And there's an absence of a magnetic field here. There is no magnetic field. So in this space right here, I cannot do QV cross B. There is no magnetic field there. So the only movement in the magnetic field are these 2 rails, and they're both moving to the left. They're both moving to the left, okay? Now these are rigid rails. What I want you to do is V cross B, QV cross B. So V is to the left, B is into the page, V is to the left, B is into the page. You'll notice that on both of these, the force is down. The force is down, okay? Well, these rigid rails can't move down. The charges could slightly separate just a little bit here. You could have positives down here at the bottom, negatives on the top, positives down here on the bottom, negatives down here on the top, positives, negatives. But imagine this. Now you've got the separation of charges on the 2 rails is identical. And it's not creating a voltage that would drive current through the closed loop. Notice that these negative and positive charges here aren't even on a closed loop. This part over here with the rails is open. So there is no induced current flow here. Maybe a slight EMF depending on the thickness of these rails, because the positive and negative charges will slightly separate, but they're not part of a closed loop, and they're not going to drive current through the closed loop. So we don't get any current here. We're not going to pick up any current by dragging the rails. Okay. The next one we're going to do is dragging a closed loop into the magnetic field. Okay. Well, the first thing that's going to enter the magnetic field is the rod. And you know that when it enters the magnetic field, just like the first 2 rods, when it moves to the right in the magnetic field, positives are going to go up, positives are going to go up, negatives are going to go down, and we are going to get a counterclockwise magnetic field, or counterclockwise current, my apologies. Great, but there's a limit to that, because notice what happens once the entire experiment is in a magnetic field. Now we have a problem. The rod on the right is going to separate charges like this, positives to the top, negatives to the bottom. But now the back end of the loop is also moving to the right. And if the back end of the loop is also moving to the right, and this is also conducting material, then the back end is going to want to have positive charges go up and negative charges go down. Well, positive charges going this way and positive charges going this way are going to fight each other. And they're going to fight each other equally, because they're equal lengths, QV cross B, they're traveling at the same velocity. They're going to fight each other equally, and we're not going to get any current at all. So this is why I said, when I did magnetic induction, I said that we're using forces now to show why the positives go up and why the negatives go down. But there is a better way. There's a more all-encompassing theorem that we're going to use to figure out which of these orientations are going to induce a current. Because you may have thought that this one was going to induce a current because you have a rod moving in a magnetic field. But once the back end of that loop enters the magnetic field, now you're fighting yourself. The left side is fighting the right side, and you're not going to induce a current. So we have a more difficult time with this one. Now, what happens if you keep moving this loop across? The moment you start to leave the field, this is pretty interesting. When I start to leave the field, okay, now that my rod is outside of the magnetic field, there's no longer a separation of charges on this guy. But the back end of the loop is still in the field, and it's still moving to the right. So positive charges go up, negative charges go down. What happens to the current inside of the loop? It flips direction, and now it's actually going clockwise because the current in the loop is driven by the voltage on the back end of the loop. When the loop entered the field, the current was driven by the front end of the loop, and it was in a counterclockwise direction. But when we leave the magnetic field, now it's going to go in the opposite direction. And you're probably seeing some mechanisms now for alternating current, where the current flips back and forth between directions. And it's definitely because of the use of loops and magnetic fields. Alternating current is a little bit easier to generate mechanically because we just need alternating magnetic fields or alternating orientations of loops. Okay, so what is it really then that's changing? Using force was a good way to show you why initially there was a EMF that was induced and initially why there was going to be current, but I would like to move to a better understanding, something that's going to be a little bit simpler to apply to all cases, even when the geometry is a little bit harder. So what was changing in the three examples where we did induce a current? What was changing? Well, in this particular case, as the rod moved to the right, I would say that the area of the closed loop was changing. The area of the closed loop was getting bigger as this rod moved to the right. Same thing was happening here. The area was getting larger as this conducting rod moved to the right. You notice that the area of closed space that's in the magnetic field, the area of closed space in the magnetic field is getting bigger, 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 bigger. And we said that that is going to induce a current. In example number 3, when you drag the rails to the left, the area is still going to get bigger. The area of the closed loop is getting bigger. But notice that that area of the closed loop does not have any magnetic field lines. So if there are no magnetic field lines in your closed loop, you're not going to induce an EMF. You're not going to induce a current. How about number 4? In number 4, I'm dragging the entire loop. So the area is not changing. The area is not changing. But as I drag the loop to the right, what is changing is B, the magnetic field. I'm picking up more magnetic field lines in the loop. I started out with no magnetic field lines in the loop. As I move to the right, I'm going to start picking up field lines and picking up field lines. But once I am fully immersed in the magnetic field, as I move to the right, the number of field lines that go through my loop is not changing. And that's why I'm not seeing an induced EMF. So very simply, what we can say, instead of using force, instead of trying to use the Lorentz force QV cross B and determine the direction of force, all that I really need to do is look at what we call magnetic flux. Magnetic flux is how many field lines are penetrating my closed loop. Okay, when you look at this closed loop here, we have field lines that are perpendicular to the plane of the loop. So this is what we would call maximum flux. All of the magnetic field lines are going through my closed loop. Here, they're still going through my closed loop, but they're going through at an angle. So here we would call the flux B times the area, magnetic field times the area, times the cosine of theta. For this one, where we have maximum flux, we just need to do B times A, because the angle between the magnetic field and the area vector is 0. All of the magnetic field lines are going through my closed loop. You imagine in this case, only the y components are going through my loop. The x components are not going through my loop. So only part of it is going through my closed loop. And in this case, this is what we would call a no flux. This orientation gives 0 flux because all of the field lines are parallel to the surface of my closed loop. So here I would say I have no magnetic field lines going through my loop. Well, how do we use this for induced EMF? Very simply, with Faraday's law. Faraday's law, it says that any change in flux will induce an EMF. So you look at your closed loop. If there is any change in flux, and flux deals with B and A, magnetic field and area. If there is a change in the area where the magnetic field is going through, or the size of the magnetic field through the area, then the number of field lines is going to change. If the number of field lines in your loop changes, you're going to induce an EMF, always. So we don't have to think about force. We don't have to think about QV cross B. We just have to look at how much magnetic field is penetrating our closed loop. If the number of lines is changing or the strength of the lines is changing, then we are going to induce an EMF. And to go one step further with that, we can even predict the direction using Lenz's law. Very simply, Lenz recognized that the current produced by the induced EMF is always going to oppose the change in flux. Always going to oppose the change in flux. Now that sounds pretty difficult, but all that it does to Faraday's law is it adds a negative right here. So Faraday's law is any change in flux causes an EMF. That little minus right there is Lenz's law. And it says that the induced EMF is always going to try to oppose the change in flux. Can I give you an example? Imagine we have a uniform magnetic field, and we take a closed loop, okay? And I move this closed loop to the right. As this closed loop enters the field, just as it enters the field, so it's not fully submerged here, it's just entering the field. Maybe it's right there, but it is moving with a velocity of v. As it enters the field, you'll see that I am now picking up more field lines that are into the page. So I'm going to say here that the field into the page is increasing. The field into the page is increasing. So I would say for certain there is going to be an EMF. There is going to be a voltage. In order to establish the direction of the current, I know that the current is going to try to create its own magnetic field. The current in the loop is going to try to create its own magnetic field that opposes the change in flux. I am picking up magnetic field lines into the page, so the loop itself is going to try to make its own magnetic field out of the page. So what direction would current have to flow for it to create a magnetic field out of the page? Well, using the modified right-hand rule, when I put my thumb in the direction of the current, my fingers will curl around the wire to show the direction of the magnetic field. So for example, let me try to do a counterclockwise current. If I put my thumb in the direction of this current, so I put my thumb up and I curl my fingers around until they're in the inside of the loop, notice that my fingers are pointing out of the page. Same thing if I put my thumb in this direction, and this direction. My thumb is going to be, or my fingers are going to curl out of the page in this region inside of the loop. So that establishes the direction of the current. It says the current is going to want to go counterclockwise to make a magnetic field that is out of the page. How about when we are fully submerged, when we are inside of the field completely? Well, once your loop gets totally inside of the field, as you move it around, the number of field lines is not going to change. So that means if there's no change in flux, then there's no EMF. There's no current. Once I'm fully inside of the magnetic field, there's no current. And then when I'm leaving the magnetic field, okay, now what's happening is you are actually losing magnetic field lines that are into the page. You're starting to lose X's inside of your loop. And if you're starting to lose X's, then your EMF is going to want to try to generate a magnetic field to replace them. The magnetic field that this current is going to try to generate needs to be into the page. So how do we make a magnetic field that is into the page, inside of the loop? We do that by going clockwise. Again, use the modified right-hand rule just to verify. Put your thumb in the direction of the current. Put your thumb in the direction of the current. Curl your fingers around like you're grabbing that wire. Notice that your fingers will curl into the page inside of the closed loop. So we will have a clockwise current to try to generate magnetic field lines into the page. So entering the field, we go counterclockwise with the current. In the field, we have no current, and then leaving the field, our current is going to be clockwise. Okay, I'll give you guys some examples and maybe some exercises that you can do at home, but hopefully this made sense. We're going to do our next live session on Wednesday, because Thursday is your spring break, so I'll hopefully see you guys on Wednesday.